So guys, let's take a look at greedy algorithms. We talked about MST and Prim's algorithms and most, so I'm going to be skipping in most of these parts which you already reviewed and go straight to the greedy algorithm phase. Let's go and do that. So we're going to be looking at Digester's algorithm and one of the most famous algorithms in terms of finding the minimum spanning tree. So let's go and take a look at that. We maintain two sets. One contains the vertices, one contains the vertices in the shortest path, another includes the vertices which are not yet visited, same as Prim's, except at the step of the algorithm we find the vertex which is the other set and has the minimum distance from the source. So I want to show this in an example. Explaining this won't actually make you understand. Let's go and take a look. Okay guys, so let's take a look. This is a very important and one of the most favorite algorithms of all time. So let's take a look. We start off at 0. So like I said, in MST, 0 is added and we have all these as 0 and we get all the others as infinite. But before that, we want to make sure which has the lowest distance. So we consider this. What is connected to 0? It's 1 and it's 7. So when 1 and 7 is actually connected to 0, what does that mean? This has the lowest distance. So what does that mean? We should go to 1. Simple as that. So we'll go to 1. So what does this mean in MST? It has 0 and 1 in this case. Let's keep continuing. So the sets of 0 are all marked as infinity like the same before. So we include 0 in the set. And then we have the vertex of 1 and 7. But instead of 1 and 7, we took the one which is the lowest of distance. That's what we consider 1. So like this in the previous example, 1 is picked since we have the lowest distance. That's what the slides are telling you. So now we consider the next distance. What is next to 1? It is the vertex of 2. But what is the distance between 1 and 2? It's 8. But are there any paths and exit vertices from 1? No, there isn't. It's only 2. So what does it give us? We are left with no choice except to go to 2. You can see here what I'm talking about. So what does that mean? This is basically 8. This is basically 4. So to go to 1, it took 4 points, and then to go to 2, it took 8. So a total distance of 12, which is marked over there. So now what does this happen? So now what happens? Think of it. So this is 12, and this is 8. Which is lower? Which is better? Which is more optimal? This, of course, since we may be thinking this may be giving us a better spanning distance. So hence, we go from 0, 1, and 7. We don't go to 2 because of the distance. So this has a lower distance rate. Which is lower? 8 or 12? 8. So that's why we add 7 here. Then we took a look at the vertices of 7, which are the vertices of 6 and 8. So let's take a distance and compare that now. So we have 7 here. So in 7, let's take a look at what actually happens here. So we have two vertices, we got 6 and 8. What happens to the distances? So we have 15 on one side and we have 9 on the other side. So what does that mean? We go to 6, obviously, since 12, 15, and 9, which is lower? 9. So we add 6 into the MST. So you can see here what I'm talking about. So now let's take a 6. We have 2 more, 15 and 11. What does this mean? So we can take any 2 paths, but since this is lower, we're going to take 5. Done. So we add 5 into the MST. Next, after we add 5, we take a look at what is the only remaining option, that is 4, so we add 4 into the MST. But guess what? With 21 points, we just lost all the things which are actually necessary. We still need to cover 2, 8, and 3. So where does the remaining points come from? So this is where we actually cut the line from here. So instead of going from 11 to 21, we take a look at the next preceding step, that is 12. So we go to 12, we take the distance, we go to 2, we visit 2 and go to 8 since it's 14. 14 is still less than 21. Then we go to 3, it's still less than 19. So what's the remaining point here? 21. So the following MST would be 0, it goes to 1, then it comes back to 7, then it goes to 9, then it goes to 6, then it goes to 5, then it comes back and goes to 2, then it goes to 8, then it goes to 3, and it comes back last at 4. So that would be the MST. So the implementation, it's basically the same. Let's take a look at what actually changed here. So we're going to use a Boolean set of special set to represent the set of vertices include the SPT. And we're going to use the SPT set V is true to whether it's located yes or not. So let's take a look. We have the basic v, except in this case we're using 9 different vertices. Then we use the minimum distance. So minimum distance has the in distance value, and it has the bool special set to locate whether it's true or not, whether the vertex is in the SPT or not. So we have the int minimum value as same as before in prims, except this one's going to change. So let's take a look. And before we had a different condition in prims, now we also have a different condition here. So the SPT is equal false and minimum distance less than min. So it's the same thing, but different parameters have changed here. Before it was a different parameter, now we're using the distance value here. Before it was actually the edge weights, if you remember correctly. So now let's consider this. We have the inprint solution, a utility function to construct a distance array. So we have the distance and the number of n. So we use the number of vertices as the maximum number output for this for loop, and actually specify each number distance to make sure we get the distance from the source. Then we're going to use a function that actually implements the Dijkstra's single shortest path algorithm, which is known as SPT. So in the single shortest path algorithm, we use the agency matrix representation. So to get that, we're going to use the graph and we're going to use the source, nothing else in these two parameters. So we're going to have the distance v, the same thing, we're going to have the bool SP set. So the output array, distance I, will be holding the shortest distance from source to I. And we have the SPT, will hold true if the vertex is yes, present or not. So rest initialize all the distances to infinity except the vertex which is first, which is now going to 0. So that's what it basically did. And the distance y is int max is infinity, and SPT is false. Then we enter source 0, like I said before, right there. We're going to find the shortest path now. Let's take a look. So we're going to use the count function and actually use the vertex v minus 1. Why is it v minus 1? Well, we already took a look at 0 and matched the first vertex of v1 to 0. So what does that give us? We cancel out one vertex, that is v minus 1 now. So we're going to pick the minimum distance vertex from the set of vertices not yet processed, that is not in SPT. So the SPT of the vertex should be false. That's what it's basically saying here. So, and u is always equal to the source in the first iteration. So u is the minimum distance from distance to SPT set, since u and v is the minimum distance here. So we're going to mark SPT of u is true. We're going to make sure that's true. And we're going to make sure we get all the edges and vertices of the picked vertex. Why do we need to get the edges and vertex? Take a look at this. If you remember from a previous example, this was, I guess, 8. I don't remember the number. It was 1, I guess. Okay, let's just give it as 2. Then we have 3 here, and we got 4 here. So this has a distance of 4, this has a distance of 3, and this is 2. What would you select? So the total distance of here would be 4, total distance would be 6, total distance would be 7. It would be 3, obviously. So it would go from 3, 2, and 3. How do we decide between 3 and 4? Well, it's actually between the minimum distance, which we're doing right over here. So let's take a look. So we update distance of v only if it's not in the special set. That means we don't want to repeat it again. So there's an edge from u to v. The total weight from source v to u is smaller than the current distance. We want to make sure it's smaller than the current distance. If it's not, we're not going to be utilizing it. So that's what we actually said over here. That's what I explained here. So first, let's take a look at this if condition. It's looking quite harsh, but let's deconstruct it. First, it should not be in the set, and it should be in the graph. Then the distance should not be equal to infinity, and the distance plus distance of u plus the graph of v should be less than the total versus distance. So this is the most important point, I guess, of the whole graph structure. Just remember that. And if that's true, then we add this. Then we add distance. Then we add dist v is equal to dist u plus the graph of u and v. We just want to make sure that it is minimum. If it is minimum, then we're just going to make it that. Then we're going to just print out the solution. We just want to construct the distance array. So we have the int main, as simple as before. We just have to add the graphs here. So this is just basically adjacency matrix stating which is which and which is that. So that would be basically 1. Let me just make it easy. 1, 0, 1, 2, 3, 4, 5, 6, 7. It would be 1, 2, 3, 4, 5, 6, 7, 8. So this would be given by this. It would be 0, 4, 0, 0, 0, 0, 8, 0. So what does that mean? So 1 is connected to 2 and a distance of 4. So that's how you basically get it. So we just constructed this example right over here. that we had to register a graph of 0. 0 is the total distance here. So the output, we can have the distance, and this is from source, and we get the nodes here. Let's take a look here. The code calculates the shortest distance, but doesn't calculate the path information. We have the shortest distance, but we don't have the path. We specify the path being in the whole of the SPT being a good set. 0, I don't remember correctly, it was 0, 1, 2, 7, 6, 8. It was something, but I did remember the last is 4. So we can create the parent array, update the parent array when distance is updated, and use the shortest path from sources of different vertices. So what it's saying is we use the parent array to actually construct the shortest path and shortest distance path here. So the code is for an undirected graph. So the same direction can be used for directed graphs as also. So a directed graph is something which is pointing to another area like this. An undirected graph is something which just connects. So 2 can go to 1, 1 can go to 2, it doesn't really matter. So the code finds the shortest distance. If we're interested only in the shortest distance from the source to a single target, we can break the for loop and pick the minimum distance which is equal to the target. So what this actually means is, so we actually calculate the distance from each and every single point to make sure that we get all the cases. If we don't want that, if we want to have only one and the last vertex, I don't remember these vertices, there was something, this was something. It was something like this. It was something like this, where this is 0, this is 1. Yeah, I don't remember. So if you only want to calculate from 0 to 4, we would just make sure that we remove the for loop for all the different iterations and make sure that target value is only equal to 4. So that's what this is saying here. So the time complexity is just the same as prims, is O of v square. For an instance list which we used as before, it'll be O of e log v, where v is the number of vertices and e is the number of edges. So that's it, guys. I'll see you in the next video. Before, I do have one more point. So the digest solver doesn't work for graphs with negative edge weights. For graphs with negative edge weights, you should use Belfort algorithm, which we'll talk about in a new video. You can check out the link in the description below. I'll see you soon.